emerging diseases.
To contain
Brings the total number of confirmed
diseases.
cases in the country.
To control the spread, testing became crucial. But how do we detect such a tiny invisible enemy? Viruses, including SARS-CoV-2, are microscopic particles that can cause widespread illness. But to identify them, we need powerful tools. COVID-19 is caused by the SARS-CoV-2 virus, one of the many viruses identified using a breakthrough technique also known as polymerase chain reaction, or PCR. PCR was developed in 1983 by Quilas, an American biochemist who won a Nobel Prize for Chemistry in 1993 for his invention. Before PCR, amplifying DNA fragments was time-consuming and labor-intensive. With PCR, a machine can produce billions of copies in just a few hours. In fact, it can happen in a test tube. So you may wonder, how does PCR work? First, we need the DNA portion that will make copies of, a buffer to put it in, and the things that will be necessary to make more copies of the DNA. We'll need primers. We'll need DNA polymerase, the building enzyme. Typically, the polymerase chosen for the job is Staq polymerase, a type of heat-resistant polymerase. It is originally from a type of bacteria that can handle and live in a really high temperature in nature. We'll also need DNA nucleotides for the DNA polymerase to build with. The PCR sequence has its three major steps. Step 1. Denaturation. Heat is what we will use in this step. This step involves the addition of heat needed to separate the two strands of the DNA molecule. Step 2. Annealing. This is when the two DNA strands that now have been separated by that heat are going to be cooled and be joined by the primers. The temperature for this step should allow the primers to bind to the specific segment of the DNA that will make copies of. Step 3. DNA synthesis. With DNA synthesis, we're going to make more copies of DNA. And to do so, DNA polymerase will begin to work on both of these strands, and it will use the DNA nucleotides as its building material to amplify the DNA. We should note that the temperature at this step may be a little warmer than the previous step. Now, after finishing one cycle of this, we now have two double-stranded DNA molecules, right? We'll repeat with the denaturation, annealing, and the DNA synthesis steps. Now, we have 4 double-stranded DNA molecules. We repeat the steps again, now you have 8. So, why? Why do this? Any technology that requires copies of a segment of DNA could benefit from PCR, but we'll highlight just 2 examples. PCR can be performed to make copies of the fragments of DNA that are found at the crime scene. Another example, diagnosis of a disease such as one caused by a virus. rRT-PCR testing for SARS-CoV-2, virus that causes COVID-19. You might have heard of one test type that uses a sample from a nose or throat swab in a PCR test. But to be more specific, this test for this virus is a real-time reverse transcription. The reason it has this fancy reverse transcription in there is because this virus uses RNA as its genetic material instead of DNA. And you have to use an enzyme called reverse transcriptase to convert the RNA into DNA. So before we can do the regular PCR steps we've mentioned, we must convert isolated and purified RNA into DNA. A specific primer is added that will bind to an area of viral RNA, and then the reverse transcriptase is used to convert viral RNA into complementary DNA. Using specific primers and a Staq DNA polymerase, the complementary DNA can be copied over and over each cycle in the familiar steps we've been mentioning of PCR. The goal is we need enough copies of the viral cDNA in order for it to be detectable. The idea being if it's a positive result, you have these selective primers binding and you have the Staq DNA polymerase making more and more copies of the viral cDNA each cycle. A certain level is needed for identification of a positive results. Thanks to PCR, rapid and accurate testing became a reality, helping us control the pandemic.